Welcome back. We are racing through this new ability to take derivatives to find instantaneous rates of change and slopes of tangent lines. Let's do a position and a velocity problem. So, position and velocity is just an example of rate of change. A falling object travels 4.9 t squared meters, t seconds after being dropped. This is true, assuming no huge wind resistance. How fast is it falling after 5 seconds? Okay, so really what we're saying here, and it helps to interpret this, is I have, actually, let's use our s that we like to use. I have a position function, s, is equal to 4.9 t squared. And I want to know s prime of 5. How fast is that falling after 5 seconds? By the way, this is also, you might be more comfortable with velocity, because the derivative of position is velocity. Okay, so to do this, in this section, while we are still doing everything by hand, we're going to take the limit as h goes to 0. You know the game now. Looks like 4.9 something squared minus 4.9 something squared all over h. Okay. Now, what are those somethings? Well, this one is going to be 5 plus h, and this one is going to be 5, right? 5 plus a little bit, and then just 5. And so the difference in the y values is what you get when you plug those into our functions. All right, if you can get that far, this becomes a big simplification game. Let's go ahead and play that game. So I'm going to use a limit law to make my life easier. I can pull out this 4.9 from the fraction, and my limit law says that's a constant. I can pull it all the way out. So this is going to be 4.9 times this whole limit. That will certainly make my life a lot easier and give me much cleaner numbers. Okay, from there it's a matter of FOILing. Keep that limit around. You don't get to ignore it. It matters. So this becomes 25 plus 10h plus h squared. Yes, your life is easier if you can FOIL faster. All over h. Looks like we got some canceling to do. This 25 and that 25 are going to go away. And this time I'm going to go a bit faster. I think if you've seen this enough, you probably can too. That this h now can cross out with that squared and this h. So only go this fast if you can really pull it off. If you can't, then really bad things happen. Oops. So 4.9 limit as h goes to 0 of, we still have a 10 on top, and we still have an h on top. It's just a 1 on bottom, or nothing at all. But at this point, now this is, now we can just plug in. This is a rational expression, and it is not 0 in the denominator, so it is continuous at 0, which means I can plug in. That's what continuity means. The second we crossed out those h's, we got something continuous. When it's continuous, we can plug in. So this is just going to be equal to 4.9 times 10 plus 0 over 1 is 10, or 49. I'm not going to worry too much about units. If you care, this is going to be meters per second, which is interesting because s had meters as its units, but then once we took the derivative, it picked up the units of seconds from t. So 49 meters per second, which is pretty fast. It turns out falling objects start traveling very fast, very quickly. You know this if you've ever fallen from a high height. Okay, really neat. I would like to try to go off on a bit of a tangent, but it is part of the course. Rate of change in general. So far, most of our rates of change have been with position, but we just saw this neat thing, and I want to formalize it. So instantaneous rate of change. If I'm taking a derivative of a function, then a lot of times you'll see this in other fields. Rather than h, they'll use a delta x for how much the x is changing. And you'll see a delta y for how much the y is changing. And what you get out is something whose dimensions are different. It takes the dimensions of y on top and the dimensions of x on bottom. And this can be a really useful way of thinking about derivatives in the great big world out there. Right? Economists and finance people often aren't worried about time. They're worried about the rate of change per unit sold. Right? How much profit do I make for each additional thing I make or I sell? And neither of those are time. But let's just go ahead real quickly and look at this. So the familiar example is time and position. If I take the derivative of position with respect to time, this is velocity. Okay, so I get out something whose units have an extra s in there from that time. And if I take the derivative again, I get acceleration. And we'll talk about this more in the future, but the point is that each time I take this derivative, now it's per second squared. My units change by this t function. This is one of the reasons why Leibniz loves this notation. So the derivative of position with respect to time is ds dt, and lo and behold, the units follow this very nicely as well. Okay, so this goes to, say, feet per second. Okay, so we're thinking about, there's lots of examples that don't have time. This one does, but really we're talking about how does changing one thing affect something else. So for instance, I'm still doing time, sorry. we'll talk about something without time in a second. If W of t is the amount of water in your pool at time t, what does W prime tell you? What does W prime of 10 equals 5 mean, and what does W prime of 0 equals negative 2 mean? This question really only works if you take a second to think about it, right? And you decide, do I know or not know? And can I put it into words? Try to put it into words. So W prime of t is how fast water is entering your pool. Something like this, right? So if W is the amount of water in your pool, W prime is how quickly is that changing? Okay, how fast is water entering your pool? And so if W prime of 10 equals 5, this is saying after, I guess I didn't give you units today. After 10, we'll say it's seconds. Maybe it's seconds, whatever units. Your pool is filling at 5, I'm just going to say units per second. Right. So if that number 5 gets bigger, it means it's filling faster. If it's smaller, it's filling slower. So W prime of 0 equals negative 2. This is saying that you're losing water, right? Water is leaving the pool. Right, and there's numbers involved too, right, at t equals 0. But a negative number would mean that water is actually going away. And so those negatives matter to us. 0 means it's level, nothing's changing. Right? If W of 0 is 0, there's no change in the amount of water in the pool. Negative means it's losing. And so really we're talking about rates of change of anything. This is part of the power of derivatives and why you need to know them in so many different fields, is because whatever your field is, if it's electricity, there's a rate of change inside of voltage, right? Or in biology, there's rates of change inside of population. Because we have this big abstract thing called calculus and mathematics, there's no reason why we have to stick to time. So there's applications of this. In fact, most applications of this do not use time as an independent variable. So take a second. Can you think of an example that doesn't involve time? Okay, that was a quick second. Hopefully you paused the video or thought about it. I'm just going to go through a couple, but they are endless. So a super common one in business and finance, profit per unit made. You want to know for each additional thing you make, will it give you more or less profit? How much? And this often changes with the number of units you make. They become more or less profitable as you make more. Here is another one. How about, very confusing, don't think too hard about this, but it's true, energy is the derivative of momentum with respect to velocity. Lots of things in physics and engineering and even chemistry, the formulas for them are, or the definitions of them are just, it is the derivative or integral, the antiderivative of something else. And there's a reason why many universities will have a physics with calculus and a physics without calculus. The physics without calculus, you have to memorize so much more because you can't just assume that someone can say, oh yeah, one thing is the derivative of the other. Okay, don't think too hard about that one. Just meant to show you that it can get pretty out there. Finally, how about like pounds gained per calorie? People monitor this in people when you're worrying about nutritional supplements, but certainly in things like mice or whatever other system you want to study where you're talking about the intake of calories and weight gained. Just a couple of examples. There are many, many more. And what we are going to do is we'll come in and out of examples, but the next thing we have to do is think about this whole new function, the derivative function, and what can knowing not just an original function but its derivative everywhere tell us about what we're studying. So that is all in the next section. See you then.